So now we're going to extend our discussion of the phase behavior to actual cooking materials so that you can see how the ideas that we've discussed so far generalize to those cases. So the simplest thing to start out with, it turns out, is fats. These are important for cooking, and they undergo readily visible phase behavior that is actually sort of simple to understand conceptually. So to get us started, what I'm going to do is start by showing you here these 4 different phase diagrams. These are one-dimensional phase diagrams, that is, phase as a function of temperature. And the first 2 are things that we've discussed now at length, that of ethanol and water, which of course have solid, liquid, and gas phases at increasing temperatures. We've discussed the fact that the different phases occur at different temperatures because of the different bonds that occur between the water molecules and the ethanol molecules. And these I'm contrasting with 2 materials that you cook with, namely coconut oil and olive oil. So coconut oil and olive oil, it turns out, when you're cooking, have 2 major phases that are important. There's a solid phase and a liquid phase. So coconut oil has a solid to liquid phase transition at about 24 degrees Celsius if you're at 1 atmosphere of pressure. So that means if you take coconut oil and put it in the refrigerator, it actually solidifies and becomes sort of a solid gook. Whereas if you heat it up a bit, it will actually become a liquid. Olive oil tends to be a liquid over a much wider temperature range, but if you put it in the freezer or cool it to around -6 degrees Celsius or below, it also becomes a solid. So it also has a liquid-solid transition. And the question that we now want to talk about is, why do these transitions occur, and how can we think about them? Now, there are many different types of materials of this sort that you cook with. So just to list a couple of more, there's shortening, sort of made by Crisco, for example, or there's much more appetizingly, there's cocoa butter, which is, at the heart of making chocolate. And these are all fats which also have liquid-solid behavior, liquid-solid transitions at different temperatures that really depend on right, that are different from one material to the other. And so again, we want to ask, why does this happen? Why do the different materials have different transition temperatures, and what is the physics that causes the transition temperatures? And I hope that you won't be shocked when I tell you that the answer to that is really the same qualitative answer that we were discussing in our discussion of simple materials before, namely, there are molecules in these fats, and the molecules both stick to each other and they jiggle. And basically, the different behaviors of the different fats are due to the different ways that the fat molecules interact with each other. And so in order to understand that, I need to tell you a little bit more about the molecules that exist in a fat. So these molecules, it turns out, the main component of fats are molecules that are called triglycerides. And they're called triglycerides because at their base, there's a glycerol molecule. And attached to a glycerol, there are 3 fatty acid chains. That's the origin of the tri in triglyceride. So these fatty acid chains can have a variety of different structures. On this fatty acid that I visualize, you can see that the shapes and structures of them are all slightly different. And it's those differences in the nature of the fatty acids that give rise to the different interaction energies between different types of fats and their different melting behavior. So there are 2 categories of fatty acid chains people call saturated versus unsaturated. You've I'm sure heard of saturated fats and unsaturated fats as having different health values for you. Well, it turns out that structurally they're really very different. And they're essentially different because of their geometry. Saturated fats you can think of as sort of long, straight chains. They have a long thing. They're called saturated because the carbon molecules in the fatty acid chains are saturated with hydrogen bonds. And so there's a single carbon bond between all of the different carbons in this chain. In contrast, the unsaturated fats are not saturated with hydrogen bonds, and because of this, there are different sort of things that can happen. There can be double bonds within the chain, or the chains can actually have a kink in them and not go straight anymore, but have a different shape. And these things, that is the double bonds and the kinks, actually cause unsaturated fatty acid chains to have different interactions than fatty acids, and this is something that we can see with just simple pictures. So let's just think about saturated fats. So those, as I said, are given by long chains. And imagine that I took 2 long such chains and I stuck them close to each other. So if I do that, then they stick to each other very well, of course, because they are they contact each other very nicely, and there are van der Waals or whatever type of interactions between the fatty acid chains that cause them stick to each other. So contrast that instead by the interactions between 2 unsaturated fatty acid chains. So those aren't straight lines, they're sort of jiggly, and when you stick them together, therefore, they can't pack as well with each other, and thus the sticking is simply not as strong. So, and the sticking is not as strong because of the different bonding behaviors in the chain. So you see we have these two different types of fatty acid chains. We have saturated fatty acid chains, which are basically straight and packed very well. We have unsaturated fatty acid chains, which are not straight and don't pack so well. And so the interaction energy of saturated fatty acid chains is therefore higher than that of unsaturated fatty acid chains. Now, given what I've told you already, you should already have an opinion about what the different melting temperatures are going to be in these different materials. So since saturated fatty acids have a higher interaction energy, we expect them to have a higher melting temperature than unsaturated fatty acid chains. It takes more energy to basically more thermal energy, more jiggling energy to rip the molecules apart. I want to now show you data for the melting temperatures of different types of fats. But before looking at it, I want to sort of point out to you that there's one other complication that can occur here, which is that since these molecules are made of chains, then different chains can, of course, have different lengths. And if you imagine that I had a very long saturated fatty acid, if I had two long ones that are stuck to each other, they're going to stick more strongly than two short fatty acid chains. And even if I were to have an unsaturated fatty acid, if I were to make it long enough, it might stick as well as a relatively short saturated fatty acid chain. So there are really different variables that are going on here. There's the question of whether the fatty acids are saturated or unsaturated, and then there's also the question of their chain length. And these are the important measures of the melting temperature of fatty acids. Now, before showing you the numbers for typical materials that you cook with, I want to first show you a simulation of the melting behavior of a fat. This is an analogous simulation to those that we showed you earlier with the melting of water. And what you're going to see from this is that the chains at low temperatures are all stuck to each other, and as the temperature goes up, they all come apart. So this table shows the different, the fat composition of different types of common cooking materials. So we have olive oil, we have coconut oil, we have cocoa butter, an ingredient of chocolate, and we have shortening. And you see from this that they all have very different amounts of saturated fatty acids. So olive oil has a relatively low percentage of saturated fatty acids, it's about 14%, whereas cocoa butter has a much higher percentage, it's about 61%. And so given the discussion of that we just had, then you won't be surprised that what we would sort of expect is that cocoa butter should have a somewhat higher melting temperature than that of olive oil. We don't actually, and we can't a priori predict how much higher it would have, because of course the amount depends on the relative chain lengths in the two different types of fats, but that's a reasonable expectation to bring in. And indeed, when we plot the phase diagrams for cocoa butter and olive oil, that's exactly what we see. So we see that cocoa butter actually has melting temperatures that are sort of in the range of 27 to 35 degrees. That's around the temperature where it melts. It melts at a temperature above certainly 35 degrees, whereas olive oil has a melting temperature that's more in the range of around -6 degrees Celsius. And so there really is actually a big difference between these two melting temperatures. Now, one interesting thing about the phase diagrams of these materials is that when we specify the melting temperature for fats, it's not an abrupt transition. There tends to be some range. The reason for that is that cocoa butter and olive oil, that is typical fats, aren't composed of fats of single chain lengths. There are actually several different types of ingredients within them. And so there's really a range over which these different behaviors, in which the melting behavior occur. If you'll allow me to make an analogy, it's actually not unlike what happens in an egg. So in an egg, there are different types of molecules that undergo different types of phase transitions, and that is the reason for, as we described before, the innumerable number of different transitions that occur in an egg. Really, in the same way, cocoa butter is a rather complex substance. It contains sort of different types of fats within it, and those different types of fats have different interaction energies with each other and different melting temperatures, and that's what gives rise to the range of melting temperatures in cocoa butter, which is something that in a pure substance simply doesn't happen. I mean, water basically goes from a liquid to a gas at 100 degrees Celsius at 1 atmosphere, and that's it. It's not a range between 95 and 105. It's 100 degrees Celsius. Whereas in a more complex material like cocoa butter, we start to see the hints of what happens when you have a material that contains many different things together.